Okay, so good morning, everyone. We're going to start with atomic physics. I know we're jumping in the syllabus, but atomic physics is a short topic. So we can get this done in the 3 2-hour classes that we are going to cover during the holidays. So we have this week, next week, and the following week to wrap up this section. So it's not a very hard topic. It's a lot of talking. It's a lot of stories. Right? And, I think there's like one equation or two equations, two equations in this entire topic. So it's a soft topic, right? Really interesting topic. Just to tell you, there's an entire section that comes on this question. For the last few years, they've been bringing question 1 on this topic, right? Which is giveaway marks because we do have a lab that basically tells you how to do that question 1 if it happens to come. So if anybody ever looks into half-life, right, and stuff. So the topics that we're going to cover, if you've read the handout or skimmed through the handout, will be atomic physics. All right, this is where we look at the physics of the atom. Then we're going to look at radioactivity, and let's touch on nuclear energy for a little bit. So it's a really simple syllabus. Right, at CAPE, it expands a whole lot. It gets huge in CAPE, right? But at this level, it's just a little touch on the topic. So any questions you all have ever heard or thought about, or anything you think you know about this topic, be sure to ask, right? Raise your hand, say when you have a question. Now for the participants, lock at the side. Right, so just raise your hands when you all have a question, or just, put it in the chat because I will see the chat. Okay, so let's start. All right, atomic physics. Okay, so this is going to recall some of your chemistry knowledge. I know some of these things you would have done in chemistry, so we can fly through a bit of this since you should know it already. If you don't, go and revise your chemistry. So the atomic model, let's read. The current atomic model consists of negatively charged electrons circling a dense nucleus. In this nucleus, particles such as protons, neutrons, and other subatomic particles can be found. Right? This is what the general accepted model of the atom looks like. We have a very dense cloud in the middle of your nucleus, and then we have the electrons that spin around, right, at high speed, forming a cloud, right, around your nucleus. So that is what we know now, as in confirmed. We've seen it, we've done experiments to prove it without a doubt. Okay, so we're going to look at how we came to discover what the atom looked like, because the atom is the building block of all matter in the universe. It's a very loud truck passing. All right, so the diagram of the atom that we know of now. It's a very loud car, my apologies. All right, the atomic model that we know now, or the diagram that we know, is called Bohr's atomic model, right? Named after another physicist called Niels Bohr. All right, so he came up with how the atom's supposed to look like and whatnot. So all these people here did a lot of work in coming up with the model that we know right now, which is our dense nucleus and our very, very, very fast rotating electrons. We do know that electrons orbit our nucleus in shells or in different energy levels. All right, as chemistry students, you all should know that the first shell has 2 electrons. How many electrons in the second shell? How many valence electrons in the second shell? 8. Anybody knows how much in the third shell?
8.
Third shell? First is 2, second is 8, third shell. Anybody happens to know? No, that's okay. I think there are 18 electrons in the third shell and so forth. And there's a reason why electrons are organized in these numbers, but we're not going to touch that in our syllabus today because again, it's out of your scope of work. So this is what we are trying to look at today. This is the model we are going to come up today with. All right, see how they discovered why the atom looks the way it looks like here. So reading, when the atom was first being investigated, the main components of the atom, which are the electrons, protons, and neutrons, had not yet been discovered. So imagine you're trying to determine what is in an atom without one, knowing what it looks like, two, knowing what is inside of it, right, and whatnot. So it's kind of an impossible task when you think about it. How can we determine what something is made up of if we don't know what it has, right? We don't know what it looks like, right? And we don't know anything about it except one basic thing. The first thing we know about electrons, atoms, is that they have neutral charge. As chemistry students, I'm going to draw on your chemistry knowledge a lot this morning. So remember how you get neutral charge. Remember the positive and negative charges that we have in our atom. Remember how we can change our charges, right? You know, if we have little less electrons, we're going to get a positive charge. And we know if we have too many electrons, we're going to have a negative charge. All right, so that's just something to remember at the back of your mind today, right? Think about how charges work. Think about your basic chemistry knowledge because we're going to pull on that a lot this morning. So let's dive into this, how they discovered our atom. So the plum pudding model, all right? I need to adjust this a little bit because I actually went and got dates this morning, all right? This came out in 1904. All right, so 1904, that was our newest model. So that's 118 years ago. So let's say 120 years ago, we had no idea what the atom looked like. We already had an idea that matter was made up of very small things that bind it together to give us everything that we see around us. All right, but now they wanted, you know, we're trying to figure out exactly what lies, all right, inside of our materials. So in 1904, this was proposed by Sir J.J. Thomson. All right, in 1904, he proposed our first model. Right now, things move very, very fast once he had that first proposal, as it moved ridiculously fast, that age of discovery, the last decade of the 1800s. All right, so like the 1890s, the 1930s. These are what we call the golden years of atomic physics, as in everything. The whole background and the whole base of the story was in these 40 years. Okay, so in 1904, the newest idea for the atom was that, now listen to this, it consisted of a ball of positive charge with random negative charges in it. So this is what they thought it looked like. It was just a ball of positive charges, well, one whole clump of positive charge with random little negative charges in it, such that these negative charges perfectly balance out the ball of positive charge. Because you remember, right, an atom must be neutrally charged. So when we have the same number of positive and negative charges, we are going to get a neutral charge or an overall charge of 0, right? These were maths and everything works together. All right, so this is one thing that they knew back then, that atoms had a neutral charge. We know that when we took away electrons, we made it positive. We know when we added too many electrons, we made it negative. All right, but everything usually had a neutral charge. So he had come up with this model, right, which was a ball of positive charge with random negative charges in it. And somebody, when J.J. Thomson had presented this model, presented his paper, which was a hypothesis, you know, he came up with an idea first. Let's come up with an idea first. That's our hallmark of physics. or science, come up with an idea, think of something first. So he had presented this model here, which was positive charge, right? So this ball itself had a positive charge without negative charges in it. Somebody had looked at that on the blackboard, right? He drew this on the blackboard, all right? And somebody said, you know, not looking like an old dessert that they call, an English dessert called plum pudding. All right, for those who looked at the recording, plum pudding is basically, folks, our black cake without the browning in it, right? So it's like a pale black cake, right? So we had that's the dessert that they had back then, and kind of looked like it. The ball, this is our ball of positive charge, and all our little raisins and cherries and prunes and whatnot look with our negative charges. All right, so imagine this guy, very respected, well-respected, well-respected physicist at this time, right? Came and presented his things to the Royal Academy of Physics and Science. And then somebody said, you know, this looked like a cake we had this morning. And for some reason that stuck forever, as opposed to his nice, good scientific model. But you know, we can look back at it now and kind of laugh a little bit, right? Because humans like to make stories. Humans like to find a simple way to describe something, right? And what better way than to describe it by food? All right, so plum pudding model, this is why we call it a plum pudding model. No self-respecting scientist would have called his model plum pudding. All right, so this is what they took at the time, right? Our negative charges, all right? And that is what we went with at the time. So let's move on. Now, J.J. Thomson had the plum pudding model in 1904. And just to go back a little bit, he himself had discovered the electron not too long before, like about 7 years before. So that would have been 1897. He had discovered the electron. Him, you know, the same J.J. Thomson. So he's a, you know, kind of big force in the world of atomic physics at the time. He was the man. All right, so they had discovered the electron. So they knew some things about the atom. They knew about electrons. They knew about atoms being neutrally charged. And they took with that and they went with it. Then we have the big experiment, the big accidental experiment, the experiment that really had no intention of changing the world of physics, as in none at all. These guys for this experiment had no clue they were going to set out to basically break open the atom in the world of discovery. All right, so we have the discovery of the nucleus. Just in the back of your head, I want you to keep thinking about neutral charge and what the atom looks like right now. You know, we have our nucleus with positive and neutral charge, and we have electrons spinning around it. We know that. Just keep thinking about that in the back of your mind. All right, so let's move forward. This is called the Geiger-Marsden experiment, or the gold foil experiment, or the Rutherford experiment. They all have the same, different names, but they mean the exact same thing. So I call it Geiger-Marsden experiment. I will always call it that because these were the guys who were doing the work. All right, it was Hans Geiger and Ernest Marsden. All right, they were master students, so probably PhD students of Sir Ernest Rutherford. All right, and Rutherford had worked with J.J. Thomson. All of these guys worked together. They were in the same general area, right, at the time. So let's read this experiment, read this topic. In this experiment, alpha particles, which are positively charged radioactive emissions, were fired into a very thin gold foil. Their passage was noted, and most of these particles went through the foil, but for a few, meaning out of 10,000 or less than 1 out of every 10,000 of these alpha particles will get deflected. According to the then current model, this should not happen. Now let's break down this little sentence and see what they're talking about here, man. Why are you there? All right. All right, so we have an alpha particle. An alpha particle is a radioactive emission, as in it's radioactive. All right, and basically what it is, it's a little packet of 2 protons and 2 neutrons. It is a little particle that has 2 protons and neutrons that fly through space at a very high speed. I think it flies through space at 1/10 the speed of light. We have done speed of light. You all should know speed of light is 3 × 10⁸ meters per second, or 300,000 kilometers per second. That is how fast light travels in 300,000 kilometers in 1 second. All right, so these alpha particles, they are very small because it's a little particle, or it's a little packet of energy that carries 2 protons and 2 neutrons bounded together, right? And it travels at 1/10 the speed of light, which is really, really, really fast. Okay, now it is radioactive. What they had done, they had just discovered radioactive materials, as in right in the late 1800s. They discovered what radioactive materials were, so they were really interested in finding out how these new little particles behave. They wanted to know how they affected the materials around them. They wanted to know how far they traveled, right, and whatnot. Remember, this is the 1800s, 1900s. Electricity had just been discovered, right? The telephone had just been invented, right? People were still, basically driving around in a horse and carriage, and those who had money had a very, very, very rudimentary car. Okay, so not much technology at the time, but they had some pretty smart guys, as in tons of brilliant people who used what they had to figure out how these materials behave. And what they were doing with these alpha particles, they just wanted to see how alpha particles affected various metals. That's all. Right? So what they were doing, they took a piece of foil, gold, rolled it very, very, very thin, and they were firing the alpha particles into them. All right? So what they did, they took these alpha particles, fired them into the gold foil, and noted where they traveled and how they traveled, probably to see if the gold foil would have slowed them down or probably absorbed them and whatnot. But what had happened, most of the particles went through as they rightfully expected to, but ever so often, a particle will hit the gold foil and get deflected, right? Ever so often, right? As in less than 1 out of every 10,000. So it's not to say it happened often, right? One will get deflected. And even rarer than that, one will bounce off the gold foil. Now, this should not have happened. They did not expect this to happen, because as far as I knew back then, atoms were a little tiny neutral charge, right? Ball of positive charge with random negative charges in it. So if I take a little positive charge, because 2 protons has a 2+ charge, and I fire that into my atom, it should just pass through because this is neutrally charged. Did I just take out my electrons? Right? I can fire my little alpha particle through the atoms, and they're not going to get deflected whatsoever. They wanted to see if it would stick. That's basically what they wanted to see, if it would stick. So they were expecting this to happen. My alpha particle just to pass through them and go on their merry way. They didn't expect this to happen, for it to get deflected. They didn't expect my alpha particle to come and bounce off it, right? They really didn't expect any of that to happen. So rather than think that they were going insane, right? They tried the experiment again. They did it over and over, right? And then they start thinking about the results that they got. You see how students like to say, Miss, we're doing this wrong, Miss, the apparatus not working. That doesn't always mean that the apparatus is not working when you don't get the results you expect. Usually when something happens differently that means something else is happening in your experiment. That means you're seeing something else than what you generally expected. All right, so they went with this. This is the whole curiosity of science. Don't accept what you always see, right? Learn to understand why it happens, and then you accept it. All right, so they saw something weird happening. Let's see why it's happening. So let's look at what the experiment looked like. All right, this is what the basic experiment looked like. We had a little lead container, a small block of radium. Radium here gives off alpha particles, which has a +2 charge. And there was a little tiny space. When I tell you a small space, like a pinprick size space for these alpha particles to fly out. All right, they would fly out, hit this very thin gold foil. And what they did, they took a photographic film, all right, and basically put it around it so that they will be able to look at the alpha particles that were coming out of the gold foil. And believe it or not, the photographic film was to protect their experiment from other things coming into it. All right, so it was mainly to protect it. It wasn't to track the alpha particles from other places. Right? So what they expected to happen, this is what they expected to happen. They expected all the alpha particles to fly through nice and undeviated, right, through our gold foil. So they were expecting to see it all flying through here. And the nice thing about alpha particles flying through the foil and hitting the photographic film, on the film, they would see a little flash of light. A little flash of light, that's all they will see. All right, and this little flash of light would indicate where the alpha particles were hitting, and they would count these flashes. Y'all, if they could check in every 10,000, back then you had to do this experiment for a long time, and they would check these little flashes of light, check and check and check, all these little flashes. So they would know where the alpha particle hit the gold foil, hit the photographic film. But what was happening? They would get a little flash somewhere else happening. They will see a little flash somewhere else happening. And believe it or not, the guy who's sitting on here handling the lead container will see a flash closer to him ever so often, right? So this was very, very, confusing, because why would this happen? Because according to the atomic model back then, right, there was nothing that made these alpha particles, that nothing would make these alpha particles move the way they were seeing. As in, why was this happening? Right? There's no reason that would happen. And it's not to say the experiment was wrong. What they did, they probably got a brand new lead container, a brand new radium sample. They used new foil, they, replaced everything and did it again. And they got the same results. Right? And if you get the same results, even with brand new apparatus and cleaning everything and making sure everything is perfect, that means your experiment is showing you something. So this is what they sat down and thought of. They sat down and thought of, this experiment, as in these little results here, are telling them something about the atom itself. This is how we have to learn to look at our apparatus and look at our results critically. All right, so let's just get some space here. All right, so if I have an alpha particle, if I have an atom here, one atom here, one atom here, one atom here, and I have my little alpha particle, which has a +2 charge, my alpha particle should have just fly through, it wasn't, it was just supposed to fly through my atoms. Right? Then they start thinking about what will cause an alpha particle, a +2 charge, to change its direction. Only one thing will do that, and that's, sorry, where does this come from? All right, there's only one thing that will make an alpha particle change its direction, and that's the indication of another positive charge. And even more than that, an isolated positive charge. The only thing that will cause this alpha particle, this little alpha particle, to move, away from its original path would be an X-alpha particle, because anybody here knows what will happen if I bring two positive charges together?
The ones go together.
They'll repel, miss.
They will repel each other, because you all, again, I hope you all know this in chemistry. If you bring two like charges together, they will repel each other. If you bring two like charges, positive or negative, close together, they will repel each other. Similarly, like for magnets, you all know this for magnets. When you bring two like poles together, they repel each other, right? As a fundamental law of attraction and electromagnetic attraction, like charges repel, unlike charges attract. So they knew back then that a positive charge will only get repelled by another positive charge. If there was a negative charge here, it will get attracted. If there was a neutral charge, as in a zero charge, it's just going to move through unbothered. So what were they seeing? At the time, they were not seeing, they were seeing this sometimes. They definitely weren't seeing this, and they were seeing this sometimes too, right? So the mere fact that they had this repulsion happening meant that there had to be an isolated positive charge in the system, right? So this is where they sat down and they thought about it. They spoke to Rutherford, and they all sat down and looked at this, right? And the nice thing too, you go to your supervisor, and your supervisor is going to take you on and say, guys, I think you all are right, right? This little positive charge here, right, should be flying through this undeviated. And if mere fact that it's going to get bounced off a little bit means that there really could be an isolated positive charge in your atom, right? So they did more experiments, right? And they then looked at one, the deviation meant that there was an isolated charge, right? There's an isolated positive charge in your atom. And two, remember we said 1 out of less than 10,000 would get deviated. So that means the chance of hitting this isolated positive charge was small, right? So if the chance of them passing through, the chance of hitting this positive charge was really, really, really small, less than 1 out of 10,000. So that meant that that positive charge that was in the atom was really small. The area that held that positive charge was tiny. So let's go back up and see what our implications of this experiment meant. 1, there was a central positively charged core of an atom, which we just saw, right? Because if this is our atom and we have our positive little nucleus, right, our little alpha particle will get deflected when it gets close to it, right? So when it comes close to it, it will get deflected. The distance between the core and the electron is very large. That is why they said less than 1 out of 10,000 alpha particles will get deflected. So that means, right, for our alpha particle to get deflected, right, it's going to have to pass lots of them. 10,000 is going to pass through undeviated until one comes very close to your nucleus, and it's going to get bounced off a little bit. And even rarer than that, one is going to come and hit it straight head on, right, and bounce off. So that's why they said the distance between the core, which is our little positive ball, right, little positive central core, and the electron is very, very large, right? There are a few analogies into that distance, right? But I'm going to use a distance that you all know of or you all can appreciate. If I use an atom, if your nucleus is the size of you, I know everybody here is a little small, different sizes, but about the size of you. All right, suppose you are the nucleus. Your nearest, no matter where you are living right now, your nearest electron, which will be probably about the size of a your pen. Compare your pen to you, all right? Mass of your pen to you, all right? Will be about 5 kilometers, 5 to 6 kilometers away. That is how far away the nucleus and the electron is. Think about how far away that is. That's pretty far, you know, guys. All right, so what we have here, this is our nucleus. These are our electrons or electron cloud, right? The distance, the relative distance between your nucleus and the electron cloud is extremely large compared to the size of the nucleus. You okay with that all?
Yes, miss.
All right, good. If it, you know, I'm trying to bring it to know, you know, values that you know of. And on the flip side of this, if my nucleus is here, meaning if you are here and your nearest electron, which is the size of a pen, is about 6 kilometers away, there is nothing between a nucleus and the nearest electron. Nothing, absolutely nothing, nothing at all. It's empty space, right? So imagine 6 kilometers of nothing, no air, no leaves, no houses, no trees, nothing. 6 kilometers all around you in every direction possible, right? Nothing at all. And atoms make up all matter on Earth and in the universe. So that's basically going to tell us that matter itself is empty space, right? If the distance between you are the nucleus, and your electron is so large and it's full of nothing, that means that everything around us is basically empty space. All right, so it kind of freaks out people when they think about it that way, but just to give you numbers, all right, I think somebody had done somewhere, but matter is 99.99% empty space. Everything around us is empty space. All right, it's not to say, you know, like atoms are hard little balls. No, they're empty space, right? Everything around us is empty space. All right, your hands, all right, this is why if you had looked at recording before, it is technically possible for a person or something to pass through a wall, all right? Technically possible. Why? Because the wall is mostly empty space. You are mostly empty space. So why do you think we can touch things? Why do you think we feel things if everything around us is empty space? 99.9%, 99% empty space. Why do you think we can touch and feel things? Anybody want to give it a try? Nobody wants to make a guess why we can touch and feel things, even basically everything around us is empty space. Why, if you try to run into a wall, you're going to slam into the wall, probably break your nose, hit your head, all right, get a headache, hope nobody saw you and laughed at you, right? Why can't we run through a wall? Why can we hold things? It has nothing to do with muscles. It has nothing to do with how heavy it is. Anybody want to make a guess? Nobody? Oh. All right. Let me tell you why we can hold and touch things and why we do not fall through the floor, why we do not fall through the earth, considering we are all 99.99%. There's another 9 in there too, you know. All right, but yeah, right? Everything is empty space. Let's just think about it. What lies on the outside of every single atom? What particle? What particle lies on the outside of an atom or goes around an atom?
The electrons.
The electrons, right? Every single atom has electrons spinning on the outside of it. What happens to two electrons if they come close to each other? We just did it. Don't they repel each other?
Yes.
Right.
Yes, miss.
So what that means that these electrons are going to cause you to not move any closer to another atom. It's going to cause these two atoms to bounce off each other. And with the collective addition of all the bouncing of all the atoms in your body, that's how we are able to prevent your hand from going through something else. That's how you're able to touch and feel things, because you are causing these electrons to move, or you are causing these electrons to bounce and cause repulsion. Anybody ever tried to bring two magnets together and you actually feel the force of those two magnets pushing away from each other?
Yes.
Yeah, miss.
Imagine that happened with trillions of atoms in your body, trillions of electrons. That is why we cannot walk through the wall, because of the repulsion of the electrons on the outermost shell of every single atom that exists. Right? It's only because of the repulsion of that. Right? There's a way to figure out how to make these electrons move in such a way that they can not repel each other. But it takes a lot of energy and a lot of physics and a lot of computing to do it. We're getting there, but not quite yet. Right? So technically it is possible. I had seen, this was Superman back as in the WB Superman. This was Superman Smallville. If anybody had ever seen Smallville, this was back in the O's. Right? He had tried to walk through a force field, right, by vibrating his body. So we have Superman, right, with his cape, right, little curly hair. He had vibrated himself so fast, right? He was able to cause his electrons to get disrupted, right? And he was able to pass through a force field, which is technically the science way of saying how you can get one material to pass through. And next one, to say it's possible right now, no, but there is something significant about matter having 99.99% empty space. Right? It's only because we have electrostatic repulsion that is why we cannot pass through other materials. So coming back to the moral of our entire story, which is the discovery of the nucleus. All right, Geiger-Marsden experiment. This is what you're supposed to take away from this entire section. 1, Geiger-Marsden experiment, also known as the gold foil experiment, also known as the Rutherford experiment. Right? Why they call it Rutherford? Because he was actually one in charge of overseeing this, and he gets the name on the paper, even though they released Geiger-Marsden, their name was on the paper. All right, all of these things mean the same thing, which is the discovery of our nucleus. What did they do in this experiment? They fired alpha particles into a very thin gold foil. They noted the passage of these particles, and the particles that got deflected meant something about the atom. What did it mean? It meant that you all have to be able to recall these in the exam, right? What are the implications of the gold foil experiment? 1, that is a central positively charged core of an atom, which we call the nucleus. There is 2, a very large distance between the core and the electron. And 3, matter is mostly made up of empty space. So this is what you're supposed to take away from the Geiger-Marsden experiment. So after the Geiger-Marsden experiment, we went from plum pudding model, which makes no sense in science whatsoever to us, obviously no. After this one experiment, which was in 1911, we went to this. Just 1 year, 1911. We went from this to basically something that we know, it looks familiar, it looks similar to what we know now. One experiment, as I said, changed everything. So let's continue reading. The discovery of the proton. All right, not too long after the Geiger-Mason experiment, Ada Rutherford proposed the existence of the proton because they already knew after this experiment that there had to be a positive charge in the middle of our atom, right? This positive charge balanced out the charge of the electrons and whatnot. So Rutherford, and this was in 1917, and so everything's coming fast and furious. We started in 1904 with plum pudding, right? And in 1911, we came up with the nucleus, right? And then in 1917, we have here the discovery of the proton, right? Ernest Rutherford proposed the existence, right? He proposed it, and afterwards they went and proved it. So it's a particle that is much heavier than the electron with a +1 charge. The proton, however, did not explain an unaccounted mass, found within the atom. Just to give you a little heads up on what we mean by much heavier, a proton is 1938 times heavier than an electron. All right, so if an electron had a mass of 1 gram, a proton was 1.9 kilograms. All right, much, much, much heavier. All right, they did experiments to prove how much heavier it was, because what they had to do was just look at gases and find out the mass of gases. All right, so he proposed that the nucleus had positive charges in it, and these charges they call protons, right? That came from the Greek word protos. Right, you all can always go and look up the origin of these words, right? Came from the Greek word of protos, which means beginning. Right, so he has positive charges and negative charges, which is similar to the story that we know now, but there is still, an unaccounted mass within the atom. Who are we missing from the story, folks? In the story of the atom, who is missing? The who?
Neutrons.
The neutron. We still have to know the neutron is missing from our story. So we're going to come down here now to the confirmation of the neutron, as then they knew something was in the nucleus, but it just can confirm what was there. Right, and in 1932, James Chadwick discovered the neutron, as he confirmed what was this extra little particle in the nucleus. All right, so in 1932, James Chadwick was experimenting with gases. And while looking at their masses, he encountered a mass discrepancy, as in there was something heavy in the atom that made atoms heavier that they could not account for at the time. All right, so let's look at it from a maths-wise point of view. Let's look at helium. Think about our atomic table at a time. My phone here? No. All right, we know that hydrogen has 1 proton and 1 neutron. No, 1 proton and 1 electron. It has no neutrons in it. So that means it only has a single proton in the middle, and we have an electron spinning around it. Then we have helium. Helium has 2 positive charges, 2 electrons. All right, so this is what happened. Right, this is what we have for helium. Then we have lithium. Now, this is where our story changes. Right, we notice a big change in the story. We have lithium now, which has 3 positive charges, 3 protons, and 3 electrons of 3 valence electrons. So we now have 3 positive charges, right? And 3 electrons in this story for your lithium. Now, looking at this, common sense wise, you would think that helium would be twice as heavy as hydrogen, because I just said that a proton is 1938 times heavier than an electron. So that means electrons don't really add too much mass to an atom, where the bulk of your mass lies is in the nucleus itself. All right, so if it is 1938 times heavier than the electron, we don't consider electrons for masses. So they assumed, or they thought, that helium would be heavier, twice heavier than hydrogen. They assumed that lithium would be 3 times heavier than hydrogen. Now, how did they determine the mass of a gas? Everybody here knows what a mole is, right? Chemistry folks.
Yes, miss.
How many atoms are in a mole? Anybody could pull it off the top of their head? Anybody? Nobody?
2.
This look familiar, folks? We ever did Avogadro's constant?
Yeah, miss.
Right, I think I heard some cobwebs and some rust fall off in our brain there just now. All right, Avogadro's constant states that 1 mole of a material, of an atom, contains the same amount of atoms. Right, so 1 mole of hydrogen will contain 6.02 by 10 to the 23 atoms, 1 mole of helium, 6.02 by 10 to the 23 atoms, and so forth. So they knew how to get moles of gases just by concentrations and whatnot, right? So they could work out how many, what is equivalent masses and stuff of gases. All right, so they realized if they had gotten 1 mole or probably like 10 moles of hydrogen, it was not 1/3 the mass of lithium. It was not half the mass of helium. What they realized that helium was actually 4 times the mass of hydrogen. They realized that lithium was 7 times the mass of hydrogen. So clearly there is something different here. We have an extra 2 times that we don't know. We have an extra 4 times here that we don't know. Where are these extra numbers coming from? Because they thought that helium is supposed to be twice. They thought that lithium is supposed to be 3 times because of the amount of electrons and protons they have. So where is this extra 2 coming from? Where is this extra 4 coming from? Now, quite a number of scientists had discovered that there was a mass discrepancy. There's something that is throwing off the masses of these materials, as in one was heavier, everything was heavier than what they thought it to be, right? So it was James Chadwick who decided to take it upon himself to find out why our materials are heavier when compared to other materials. Why? Where is this extra mass coming from? So let's read this again. Right, in 1932, James Chadwick was experimenting with gases, and while looking at their masses, he encountered this mass discrepancy, right? The 4 instead of the 2, the 7 instead of the 3, right? And it went down so far, right? So if helium only had 2 protons compared to hydrogen's 1 proton, it should then be twice as heavier, but it was in fact 4 times heavier. Similarly, lithium should be 3 times heavier than hydrogen, but it was 7 times heavier. With further investigation, he concluded that there was a particle of equal mass to the proton with no charge, as in there was something in the nucleus that was very heavy, that was affecting the mass of our atom, that did not change the charge, or the charge did not affect it. So he called this the neutron from neutral charge. The number of neutrons in an atom is not proportionate like protons and neutrons. We know for a neutral atom, we must have the same number of protons and electrons, my apologies. But neutrons don't have to be the same number. There are different numbers of neutrons in an atom. By changing, now this is where the story gets interesting. Now you're gonna think, okay, it's a heavy particle in the nucleus with no charge. So it just sitting on there, adding weight, adding mass. What is its purpose? All right, further on, and then this is where Einstein came into the story, but we'll get to that later. All right, by changing the number of neutrons in an atom, we can destabilize the energy balance. This heavy neutron is meant to maintain the energy balance of your atom. That is what it's there for, right? Our protons are there to give us positive charge. Our electrons are there for negative charge and for bonding. But you see this neutron is there to balance out the energy in your atom. And if we change the number of neutrons in an atom, we can destabilize the energy balance and sometimes create radioactive materials, right? So even though this neutral charge here, right, has no charge, I think it's not going to do much, no. By changing the amount of neutrons, we can go from a nice, simple, calm, unreactive element to a radioactive one. All right, so you think something, you know, it really does add up to how things change and behave. All right, so we're gonna come up to, do I have isotopes? No, I didn't do isotopes in here, but you all should know from chemistry. Anybody knows what an isotope is? It's somewhere in the back of your mind.
The same number of protons, but different neutrons.
Same number of protons, different number of neutrons. All right, sorry. So we're going to look at this in a little bit. All right, let me just pause the recording for a sec. Okay, so we are going to continue with atomic notation. All right, again, you all as chemistry students, you all should know this. I'm not going to assume that everybody does or whatnot, but let's move forward. So atomic notation, it is important to record the number of major particles in an atom. What are major particles? Electrons. Really? Seriously? All right, we have electrons, protons, and neutrons. Those are our main particles in the atom. So let's go forward and see what we have. We have on our atomic number, which is given by a capital Z or Z, depending on how you pronounce it. All right, this is the number of protons in a neutral atom. There should be equal number of protons and electrons in a neutral atom. So the easy way to remember, Z means the number of protons. Mass number, which is given by a capital A, this is the number of major particles in your nucleus, which is the sum of protons and neutrons. This is otherwise referred to as the nuclear number. So A is equal to your protons plus your neutrons. And then we have our element symbol X. This is a letter or two used to represent the element. Sometimes these letters are directly from the words itself, you know, like hydrogen, helium, lithium, silicon, carbon, oxygen, right? And other times they come from the Greek or Latin equivalent, like sodium, Na, potassium, K, gold and silver, Au and Ag, right? Sometimes they come directly from the word and sometimes they come from the Greek equivalent or Greek letter to use behind them. If I were you, I would go and look up and see why some element. So what is the base word or the base background reason for, you know, things that have in the same letter as the element? There are really some cool stories out there, right? Pb is lead, right? Sodium is Na, and whatnot. So this is my little homework for you, not official homework, but just, you know, curiosity's sake. Read up on why a few of them have different letters. So the general atomic symbol will look like, we have X, A, X, Z, right? Where X is your symbol for your element, A is the mass number or your nuclear number, and Z is your number of protons. So in something like this, where we have neutral elements, so you can always add here your charge. You know, that is if you have a positive ion or negative ion, you know, your cations and your anions, right? That's where we refer to over here. But in physics, y'all, we really don't talk about cations and anions very often because it doesn't really play a part in the things that we're looking at, right? In chemistry, it's really important when you have to deal with ionic bonding and those things, but in physics, not so much. We don't really talk about cations and ions very often, but we should know where we record our charge. So here I have helium. Just in this notation of 42He tells us a whole bunch of things. One, we know that the element is helium. I know this is our mass number and our atomic number, mass and atomic. Right? Our mass number means it has 2 protons, 2 neutrons, and 3. From our atomic number, we know that it has 2 protons. And you could kind of guess too, if it's a neutrally charged atom, sorry, it also has 2 electrons. So this notation by itself tells us a lot of things. Let's try this here. 12C6. Number 1, do we know what element is C? Come on, chemistry students.
Carbon.
Carbon. All right. How many protons and neutrons does it have? Let me just take this out a little bit. All right. How many protons does it have? Anybody else? Put it in the chat too. Let's go through this again. We have our symbol, which is C. We have the number at the top. This number at the top is your mass number, which is your number of protons, plus your number of neutrons. And then the number at the bottom here is your atomic number or the number of protons. So that means that we have, very good. That means that we have 6 protons and 6 neutrons, and the number at the bottom here told us that we had 6 protons. And remember, I told you, we said before, the number of protons and neutrons do not have to be proportional to each other. It is not necessary that an atom has the same number of neutrons and the same number of protons. Some atoms have different numbers of neutrons to protons. All right, let's look at the next one here. Sorry if I erase fast, but you all can do that pretty quickly. I have Be94. 1, 2, 3. What? Anybody could recall what Be is? What element is Be?
Beryllium.
Beryllium.
Beryllium, right? It's easier to come up with part 3 than 2. How many protons are there in beryllium?
4.
4. All right, so we have 4 protons, 4 protons. How many neutrons do we have in beryllium now?
5.
5 neutrons. All right, so it's just a game of adding and subtracting and whatnot. Let me try our next one here with you all. Let me pull somebody from the table. This should get a little bigger. All right, pulling from here. I have what element is Na?
Sodium.
Sodium.
Sodium. How many protons are in sodium?
11.
11.
11. So if protons are 11, how many neutrons are in sodium?
12.
12.
12. All right. So you now notice, now we can go to our periodic table now and be able to look at the data in your periodic table and know how many protons, neutrons, and electrons we have. So I have here, these are really nice table. I'll probably send it to you, but there are tons of tables you can download, right? A really nice table for chemistry students. What it does, it tells us our atomic number. Remember, your atomic number is the number of protons plus neutrons. Atomic weight. Oh, wait, no, atomic number is number of protons, sorry. Right, atomic number is the number of protons. Let me just get a smaller pen. All right, so this is your number of protons. Your atomic weight, folks, is basically the mass of your entire atom, right? And when we want to get the number of protons and neutrons, you just kind of round it off to the nearest number. But this is a really detailed table. Look here, we have the atomic weight of hydrogen being 1.008 as opposed to just 1 proton, because there are little things that add up to the mass in an atom. All right, so it's a really detailed table, but when you want to determine what's your atomic weight, just round it off to the nearest whole number and we get our stuff. All right, so I have here your atomic number, which is your number of protons, all right, and your number of electrons in a neutral atom, your symbol, your atomic weight, which is the number of protons and neutrons, the name, so you have the names in here, and the electrons per shell, which is pretty, good for a chemistry student. So here you have lithium. I don't know if you all can see it. It has 2 electrons in one shell, 1 in the next. Beryllium, 2 electrons in one shell, 2 in the next. Look, we have sodium here, 2 electrons, then 8 electrons in the next shell, and then 1 electron in the further shell. So it's a nice little one for chemistry students. All right, so we can just look at this anyway, and look at our numbers involved in our atom and in our element. All right, so here I have it broken down into solid, liquid, gas, unknown. There's some things that we don't know. Alkali metals, alkali earth metals, transition metals, lanthanides, actinides, right? These different types of elements that exist, right? It's broken down to a whole bunch. We can look at something like, pretty sure you all have heard of nickel, iron, nickel, cobalt, copper, zinc, right? So it tells you how many protons are in copper, 29. And here you can round this up to 64. So you can look at how many neutrons are in there, right? We have gold and silver, right? 79, 47 electrons or protons, mercury, and whatnot. All right, so you'll find a table, or I can send you this one, a nice large version, but it should be easy to see in the Word document. All right. As chemistry students, you all should know the first 20 elements by heart. I hope you do. All right. It's unlikely they ask you to learn more than that. So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. All right. Know your first 20. All right. Moving on. Atomic numbers. Not atomic numbers, isotopes. Isotopes are atoms with the same proton or atomic numbers but different mass numbers, meaning their number of neutrons vary. That is all you need to know about an isotope. They have different numbers of neutrons. In nature, some elements have stable isotopes, right? More complex atoms lose stability when their mass numbers change. So when you have a big atom, we talk about complex atoms, like once you start going past calcium, once we start going past calcium, right, these are big atoms. All of these are really big atoms, and because they're large, they are less stable, right? Try building something with only 6 blocks. Right, 6 building blocks. It's going to be pretty stable, right? You can build something with 6 building blocks and it's not going to fall easily. You try building something with 108 little building blocks. Somebody just has to walk past that and it's going to fall very easily and very quickly. So that's why big atoms tend to be not as stable, right? Not all the time. I'll come to the, what stable atoms are in a while. Big atoms tend to have a lot more complex energies involved with them. So the instant you take away a neutron, it is going to destabilize your atom, and the chance of you getting a radioactive isotope increases. But we're doing radioactivity next day. So this is all you're supposed to know. Isotopes are atoms that have different numbers of neutrons. And the more we change the number of neutrons, the less stable our atom becomes. Why? Because remember, neutrons are very heavy, right? Little particles. And this heavy particle here maintains the energy balance of your atom. Numbers at a glance. These are just numbers we should know, right? We're gonna not talk too much about this as yet. When we reach nuclear energy, we'll speak about it. But because we're looking at very small charges and small materials, right? We developed something called unified atomic mass. Right, this is a symbol to represent a small mass. So we have here 1 U represents 1.7 by 10 to the minus 27 kilograms. Right, that's a really small number. So we just have this number standing in for calculations, but we're going to go into unified atomic masses when we start doing nuclear energy, which is the 3rd class from now. So particles, so at the end of today's class, these are what we know. We know about electrons, protons, and neutrons. We should know the symbols of an electron, which is a common E. The symbol for a proton is a common P, symbol for neutron, common N. Charge of an electron is -1. Charge of a proton is +1. Charge of your neutron is 0. And when you compare these masses to each other, an electron to electron is 1, obviously, because all electrons are equal, right? They have the same mass and the same charge. A proton is 1836 times heavier than an electron, and a neutron is slightly heavier than a proton, right? And it's 1839 times heavier than your electron. Okay, so these are just what we should know by the end of today's class. All right. We're going to look at charges when we start doing electricity. All right. So just a number. Again, this number you get in your exams. All right. You usually get these numbers in exams. All right. What these numbers are. So it's not, don't fuss too much on learning them. All right, so that's our class for today. Just to recall, we looked at the evolution of the atomic model, which started up with our plum pudding model, just going up to the top. All right, we started with J.J. Thomson's plum pudding model. Then they discovered the nucleus with the Geiger-Marsden or the gold foil experiment. Then we had the discovery of the proton by Ernest Rutherford. After the proton, they confirmed what the neutron was, and what the neutron, the main thing to remember about the neutron, it presented something called a mass discrepancy. It made atoms heavier than what they expected it to be. So that's why it was important to determine where this mass came from. And even though your neutron has no charge, it is important to maintain the energy stability of your nucleus and your atom. After that, we're going to look at atomic notation. So you have to know your notation well. You have to know what these represent. You have to know where you find your symbol for your electron, for your element. You have to know your mass number, which represents the number of particles in the nucleus. Your atomic number basically tells you how many protons you have in your atom. All right, so you have to know how to work out these numbers. Please write this down and learn how to work this out. Your general periodic table, your isotopes, and what all your components look like. All right, so that's it for today's class. The next class we have, which will be next week, Thursday at the same time, we're going to look at radioactivity and everything in radioactivity for this level. All right, so we're going to stop the recording here and I'll still speak to you all on the side.